Hi everyone, welcome back to Data Cadence. My name is Rahul. I work as a senior applied research scientist, and in this video, we are going to talk about why re-ranking is such a crucial step in improving the performance of a RAG system. Now, re-ranking is one of the most simplistic things that you can do in order to achieve a lot of performance boost when it comes to building your RAG architectures. It's a concept often asked about in data science and machine learning interviews, and understanding it thoroughly can boost your grasp on how these RAG systems work. And also, if you're applying for a Gen AI based role, so knowing these things about something as fundamental as RAG really helps you. So without further ado, let's begin. So before even talking about re-ranking, let's first talk about what does a typical RAG architecture looks like. Now, do note that this is a pretty naive architecture that we are going to discuss here. RAG architectures have become complex and sophisticated over time, and for good reasons, of course. But let's start with a simplistic, naive RAG architecture. So you have your original documents here. You break it up into chunks, and out of those chunks, you use some sort of embedding model to create embeddings. Now, a lot of levers come into play when we are talking about RAG. So one of the things could be how do you chunk your documents? So there are often multiple strategies. There is a fixed size chunking, there is a semantic chunking, there is a document specific chunking, and there are lots of things that can be applied. But for now, let's assume that we broke our original document into chunks, and then we use some sort of embedding model to create the embeddings. And again, embedding models also comes with a lot of variety and choices. So you could use open source embedding models from the Hugging Face hub, or you could use the proprietary ones, say for example from OpenAI and so on. And you build those embeddings, and then these embeddings are often stored in what we call as a vector database. So vector database would basically be more efficient in terms of performing things like approximate nearest neighbor search. And again, how they do that, there are algorithms like HNSW, that is hierarchical navigable small worlds, and all of that. So we're not going to go into that, but once you create these embeddings, you typically store them in some sort of vector DB. And on the other hand, there is a user query that comes in from the user, and for that also you use the same embedding model to create the query embedding. And now you do an approximate nearest neighbor search based on some sort of scoring function. So say for example, you consider cosine similarity, and you do some sort of scoring to retrieve the top k relevant chunks. So say here I retrieve say chunk 1, chunk 4 and chunk 7 based on the maximal cosine similarity between my document embeddings and my query embedding. And now typically these are fed into the LLM in order to obtain a response. And just for you, if you are a very much beginner in this particular domain, so why we do RAG? So LLMs are great at answering questions on basically the content on which they have been trained. So if you train your LLM on a vast set of data, they are very good at answering questions related to that particular domain. But if you ask any question around the data on which they haven't seen during the training phase, then that's where they sort of fail and don't work really well. And organizations these days have a lot of proprietary and private data over which they want to do some sort of Q&A or some sort of query, and then they want to retrieve the most relevant answers based on all of those documents. And these are often huge. So for a big company, they have a lot of internal documentation, CRM systems, SQL databases and all of that. And that's why RAG comes into play, that how you could leverage the power of these modern LLMs over your personal data in a localized fashion. So that's the whole idea behind RAG. So the idea is that along with the query, you also feed in the context or the retrieved context that you have retrieved using what we discussed. You pass it to the LLM. LLM takes care of the query and understands the context that you have retrieved, and it gives out a response. Now, where does re-ranking comes into the picture? So this is the initial retrieval that we do using embedding similarity. And here also is this embedding similarity could be based on a semantic search, that is you use dense embedding vectors to find out. You could also do some sort of lexical or keyword based search, or these days you could do, which is more popular, is what we call as a hybrid search. So that is combining the results from both of these or even multiple of these using something known to us as RRF or reciprocal rank fusion. We'll talk about that in some other video, but this is how the entire thing works. Now what re-ranker says is that once you do this initial retrieval, say chunk 1, chunk 4 and chunk 7, you need to find a way to re-rank these, and then maybe you add another additional step here. So let's say you have these three. So after re-ranking, say you end up with something like chunk 7, chunk 4 and chunk 1. So you decide that once you re-rank, so this is the relevant order that should come in. So this is where the re-ranking step sort of fits in. And then this re-ranked output is what goes to the LLM, and then it consumes that and gives you the response. Now, before we even talk about how re-ranking is done and you gain some sense of why it's essential, we'll talk more about that. But first thing we need to understand here is bi-encoders and cross-encoders. And I do have a very in-depth article explaining both of these, so you can basically visit this Medium article that I've written a while ago, and then you can understand more about cross-encoders and bi-encoders. I'll talk briefly about what they are and how they work. But I think this article will give you a much more in-depth view in terms of how these two work. It's not a very long article. You can definitely read through it. I will include the link in the description. But yeah, let me explain what are bi-encoders and what are cross-encoders. So when it comes to encoding your textual information into some sort of embedding, so you do have two types of architectures that are available, bi-encoders and cross-encoders. In bi-encoder, what you typically do is, say you have two sentences, sentence A and sentence B. You would encode these separately using the same transformer architecture. Say you use some sort of BERT architecture and apply pooling on top of that. Pooling because we are not dealing with individual words, we are dealing with sentences, so we need some sort of aggregation. And you basically encode these two separately and you end up with separate embeddings, say embedding A and embedding B. And then you find out things like cosine similarity to understand how similar these two are, right? So this is how a bi-encoder typically works. You have two different sentences, you encode them separately using the same transformer architecture, and you end up with a different embeddings for both. On the other hand, what a cross encoder would do it, you first of all concatenate your two sentences, say sentence A and sentence B. Then you give it to a transformer based architecture, say for example BERT. And then whatever embedding you end up with after concatenating these two, you throw it to a classifier and then use some sort of scoring function to end up with a score between 0 and 1, talking about how these two are doing when it comes to the concatenated input of sentence A and sentence B. So of course there are certain differences when it comes to bi-encoder and cross-encoder. So bi-encoder is often pretty efficient for large-scale retrieval. You might ask why. So if we take the example of a naive RAG architecture, so what you can do is, if you have sentence A as your query and sentence B as your documents, so these documents you can pre-compute and store them in a vector database like we mentioned. And once you have those pre-computed at runtime, you only need to embed this particular query, the user query which comes in, and then use things like approximate nearest neighbor search to find out the most relevant documents. So definitely bi-encoders are pretty efficient when it comes to large scale retrieval. They are also scalable for the same reason that we discussed above, and therefore it makes them very good for the real-time use cases where you need to perform searches real time and all of that. So that is there, but of course the bi-encoders do come with a lower accuracy because they are unable to capture the joint interaction between your two documents. In the case of RAG, it could be query and the documents. And of course there is a context loss also that comes in. So they do come with a lower accuracy, but they are extremely fast and efficient and they can scale really well. When it comes to cross encoders, so cross encoders often have higher accuracy because they are able to understand the joint interaction between the query and the documents, and they are effective for tasks requiring fine-grained understanding of input pairs. So if you want to gain some sort of understanding of the joint interaction between your query and your documents, that's where cross encoders play a pretty crucial part. And of course that comes at the cost of latency, so they are computationally pretty intensive, therefore they are slow, and cross encoders are not scalable and therefore not suitable for real-time use cases. So based on all of these, by now you would have gained an understanding that when we are doing the initial retrieval, we use something like a bi-encoder because that's pretty fast, gives you a candidate set of documents, the top k retrieved documents that you can use. And when we are doing re-ranking, we use the cross encoder because that can help you achieve higher accuracy. So let's go a bit more in depth. So when we talk about the initial retrieval, so why do we use a bi-encoder? We already talked about that. The primary reason is the latency and the scalability. So the documents are pre-encoded and often stored in a vector DB like we discussed. And the model doesn't need to reprocess every time a new query comes in, making it very efficient and scalable. And that's why we use a bi-encoder for the initial retrieval. But, and I say the but in capital letters, the bi-encoder doesn't model the interaction between the query and the document, which limits its ability to fully understand the context. And that's one of the major drawbacks. And that's where re-ranking comes into the picture. So why do re-ranking with a cross encoder? So like I mentioned, re-ranking with a cross encoder is giving it the ability to understand the joint interaction between the query and the documents. It jointly encodes the query and the document, allowing to better understand how the terms in the query relate to the content of the document. And this ability to process the query and the document together provides a much deeper level of understanding and the relevance estimation. And then you might ask, why does re-ranking help? So we understood that we use a cross-encoder to perform this re-ranking operation, but why does it help in the first place? So the bi-encoder stage provides an initial coarse-grained retrieval, but the re-ranking with a cross-encoder boosts the quality by considering finer details in the relationship between the query and the documents. And that's what we have been talking about for the past few minutes. And think of re-ranking as a quality control, because the output of your LLM heavily depends on how good your retrieval pipeline is. And the retrieval in the generation often work in tandem. And if you have a really good high quality retrieval pipeline, your generation is going to be top class, assuming you have a decent quality LLM. And then if I were to summarize, so re-ranking enables the system to firstly correctly capture the nuanced meaning and improve the match between the query and the document, filter out the documents that may have been retrieved simply due to the keyword overlap but lack true relevance, and then prioritize the documents that are contextually rich and closely aligned with the user's intent. And that's one of the reasons that you might want to consider re-ranking as a part of your RAG pipeline. And like I mentioned, re-ranking could be viewed as a minimal effort and a high impact improvement in your RAG pipeline. So you do have minimal effort and maximal gain. So re-ranking is one of the easiest ways to boost performance, because you don't need to retrain your entire RAG system from scratch. You can simply add a cross-encoder model on top of your bi-encoder retriever, which requires minimal addition training compared to a more complex strategies like end-to-end model fine-tuning. And in case you haven't checked about what is the difference between prompt engineering, fine tuning, and RAG architecture, so I heavily recommend you check the video in the I button where we have talked in depth about when you should consider each one of these approaches. The second one is fine grained relevance scoring. So while the initial retrieval gives you a broad set of documents, re-ranking applies a more fine grained relevance scoring. This means that you don't have to deal with overly complex retrieval mechanisms upfront, yet you still get a much more tailored set of results for your query. The third one is improved precision without slowing down too much. So like we discussed, re-ranking strikes a balance between speed and precision. The initial bi-encoder retrieval is fast, while the cross-encoder re-ranking, although computationally more intensive, is only applied to a small subset of documents. This ensures that you get a high quality results without significantly sacrificing the response time, which is pretty much crucial for real world applications. And then the last one is adaptability. So re-ranking can be applied across a wide range of tasks. It need not be restricted to RAG architectures. It can be applied on things like question answering, document retrieval in general, and that's how you can use re-ranking. So if I were to conclude, re-ranking in a RAG system isn't just a luxury, it's a necessity for getting top tier performance. And by combining the speed of a bi-encoder with a deep and context-aware insights of a cross-encoder, you get the best of both worlds, that is fast retrieval and high quality, and therefore relevant results. So if you're looking for a simple, impactful way to boost your RAG performance, re-ranking is one of the easiest solutions out there. And it's a part of almost every RAG architecture that you see these days. And it's a pretty important interview question, especially for Gen AI based roles, because a lot of people know that re-ranking is a part of the RAG pipeline, but when asked that why re-ranking is done and how does it work in the first place, they are not able to answer that in a much detailed way. But hopefully now you understand why re-ranking is essential and how it helps the entire RAG pipeline. So I hope this video gave you some sort of insights. If it did, please consider liking this video, and please subscribe to this channel and share this video with people whom you think might find it useful. And I will see you in the next video then. Until then, stay safe, take care, and keep learning.